Okay, right now we're going to continue on here now that we have hopefully a reasonable understanding of the unit circle. And I want to point out some things that are in Trig textbooks. In our book right now, this happens to be on page 373 in section 6.2. And I'm not sure if that imaging is going to show up very well on the DVDs or not, but we'll see. You will see tables, charts like this in textbooks. And if I was brand new taking trigonometry, I would go crazy if I was just trying to read this book and learn trig. So I've been showing you some techniques of how to have some mental imaging going on, because I would not be able to just flat out memorize a chart like this. Okay? I think most of you would have to be challenged by that. If I similarly, if I turn the page, now here is something that I think you should be comfortable with based on what I talked about earlier, and I'll try to zoom in a little more on that. This is very important up here. If I can get this set up properly. There. These are some definitions that we want to, or theorems that we want to make sure that we understand clearly. And I'm going to come back on the board to make sure that we have these ratios clear in our mind. If we take our unit circle and we are at some central angle theta with our unit circle, and we scale this out like I mentioned in a previous session, then onto our xy axis system, and we then change this radius on this circle to be something called r, then this is clearly the y reading of this point over here, and this is the x reading here. Now, based on the definitions that we've learned earlier, or in this theorem, is the sine of the angle happens to be y over r. And on our unit circle, the scaling brings that down where the r becomes 1, and so the y reading is the sine of the angle if we use our unit circle. The cosine of the angle is x over r. The ratio of the sine of the angle divided by the cosine of the angle is then this complex fraction you see here, and you multiply numerator and denominator by r, and you lose the r, and you get y over x. Y over x on the picture is the tangent of the angle. The other three ratios are the reciprocals of these three ratios. And I mentioned that previously. Okay, we'll focus on those later. These are the three most important for us in trig. But we will use the other ones and we'll spend more time with them later. Okay? So you kind of have to get those definitions in your head. Now, my preferred approach to teaching this material at this point is to start developing the actual graphs, because you can see a lot of things from the graphs. And in this particular section of our book, they have a multitude of properties that they are kind of listing and developing there, but they don't have the graphs available to us until the next section of the book. So, I think what I will do in trying to keep with the flow of our textbook is I want us to utilize the unit circle to help us understand some of the properties. So the sine of our standard angle then is going to be the y reading, isn't it, on our unit circle, like we've been practicing. The cosine is going to be the, I'm going to leave a little space here. The cosine is going to be the x reading on the unit circle. Now, we all should be okay with that based on what we talked of previously. Okay, so we have, I want you to keep in mind that these are points up here, x, y, which correspond to points which happen to be cosine of the angle shown here, and the y reading is the sine of the angle. As the angle changes, watch this. We did this the other day, and I did it with my umbrella. The y reading you see at 0 degrees is 0. The y reading grows to a value of 1. Then it falls back to 0. It goes negative to -1, and then it continues and comes back up to 0, doesn't it? And then it starts over. So does it make sense to you that the sine starts repeating itself if you let that angle change enough? Make sense? Okay. So does it make sense to you that the sine of the angle is the same as the sine of the angle if I added, like say I have this angle right here, shown here. If I added 360 to that, I'd be right back there and have the same reading for the sine? That should make sense to you, visually or mentally. And so we can say, and that can be either degrees or radian measure. So in the book, you'll see a statement something like this. The sine of the angle is equal to the sine of theta plus 2 pi, or that could be 360 degrees if you were in degree measure. So the sine function starts repeating itself every 2 pi. Not too tough. We could check that with a calculator, which we'll do in a couple minutes. We'll take a sample angle, and we will add 360 to it or 2 pi to it, and we'll see if we get the same sine readings. Okay? Let's try that with a cosine. The cosine is what part of this picture? It's the adjacent side, or the x reading, isn't it? Right here. Isn't this our cosine? Okay, the x reading is the cosine. And so at 0 degrees, here goes the marker again. At 0 degrees, the cosine is, everybody see it? It's 1, isn't it? And what's happening as I move the angle up towards 90? What's happening to the cosine? It's coming down, isn't it? Towards 0? The x reading? And when I go past 90 degrees and head towards 180 here, the x reading is growing negatively, and it's heading towards -1, isn't it? And then when I get back, and then as I continue on down into the third quadrant here, the x reading there is coming back up towards 0. And then think of the x. And then the x is continuing to grow towards 1 when you get to 360. So if I started at some angle theta, like I did up here with our sine, notice that the cosine also starts repeating itself after 360 degrees. So the cosine of theta is equal to the cosine of theta plus 360, or 2 pi, if you're in radian measure. Important property. Okay. We call that amount of angle necessary to start repeating itself in trig, we call that the period. Not much different than the period of the lunar cycle, 28 days or so. Starts repeating, the phases of the moon start repeating after 28 days. Okay? So the word we use is the period, okay? Which is the amount of angle necessary for the particular function to start repeating itself in its behavior. Okay. Let's look at tangent. The tangent is, we spoke of that earlier, as the y over the x Or if it's in standard angle form, we can simply be thinking of the what from beginning algebra? The slope of the terminal side. Y divided by x is the slope of this terminal side where the angle happens to be, where this terminal side happens to be pointing. Okay? So watch what happens. We have this sample angle here. We have a slope, some slope value, which is the tangent reading of the angle. Let's write that down. Okay? Now, watch what happens with the slope. The slope starts at 0 degrees at, what's the slope there? Or the tangent of 0 degrees is? Slope is 0, isn't it? Okay. And you have to know this stuff from your algebra background. Okay? As the angle grows, what's happening to the slope? The tangent values, the slope values are growing towards, well, towards 1 here at 45, but then you go beyond 45, like up here, and they're bigger than 1, aren't they? Yeah. Bigger than 1, and they continue to grow till they become bigger and bigger and bigger, until it becomes vertical, undefined. So they head towards infinity, don't they? Right? Now watch what happens when I go past, remember it's y over x, it's y over x. Watch what happens when I go microscopically past 90 degrees. Huge negative. Huge negative number. Made a transition. When you go vertical, the tangent makes a transition, illustrated here, from positive huge numbers to huge negative numbers. It's kind of like Star Trek, you know, where they do a warp speed or something, all of a sudden they jump through the universe or something, and all of a sudden we're at the other end or something, coming the other way. Okay, so kind of thing like that going on here. So we blow up, and the tangent values rise from 0 towards infinity. Then all of a sudden they jump to huge negative numbers, and they're actually coming up, aren't they? Now we're at -1 here. With me? Thinking slope. To 0. And continuing to come up until I'm down here. Oh, look, what's interesting about this? It's the same tangent value over here. This angle has the same tangent value as our sample angle shown back there. Right? Same slope. Same y over x reading. So, if I took theta and I added 180 degrees to it, or pi radians, my tangent readings would start repeating themselves, wouldn't they? So, I can take my stick and I can hold it in the middle here. Do you see that the tangent of this standard angle, where's the camera? Which one am I at? There, okay. This standard angle right here has a tangent reading, and that's the same as this, the tangent of this big angle here. So the period of the tangent function is what? It's not 2 pi or not 360, it is only 180 or pi. It's only 180 or pi. So the tangent of the angle is the same as the tangent of theta plus pi, or theta plus 180 degrees. So those are some interesting properties. Okay. Mental imaging, again, is the way I remember those things. All right. What I'm doing is I'm trying to page through our text to make sure I don't forget any of these important properties. Here are some other ones. What's the input? Here's our sine function, right? What's the input to this function? Theta, the angle, right? We have to set the angle to figure out what this result is, don't we? We have to set the angle to figure out what this result is. So this is our input. Now, what happens to those input values? The input values change, and they could be anything, couldn't they? Any angle. They could go past 360, or they could go negative on us, couldn't they? Go the other way. Okay. What about the output values? The output values are the calculated value of the sine of the angle, aren't they? How do they vary? In other words, what kind of values can you find for the sine of theta? How large can they get?
All the way up to 1 and then
Yeah.
back down to 0 and all the way up to -1. And
Down to -1, right? So they vary, those output values vary between -1 and 1, don't they? Think of range. Think of range from your college algebra background. How low can those y values go? -1. How high can they go? Up to 1. So these things are trapped, the sine readings are trapped between -1, from -1 inclusive, up to and including 1. And we oftentimes will write that in interval notation in this form. It's closed interval. What about the cosine readings? They can vary, those are the x readings on our unit circle. They can vary from -1 over here at 180 degrees all the way over to +1, can't they? And they can't exceed those values, can they? They can't go outside that. So the cosine values, let me write that down here, the cosine values are trapped between -1 and 1, including the endpoints, or in interval notation, -1 to 1 as well. How about the tangent values? The tangent values can go as low as, look at what I'm doing with my marker, -infinity, right? They can go as low as -infinity. You never can actually get there though. And they go as high as +infinity. So the tangent readings can vary, can't ever get there, so they're open intervals from -infinity to infinity, or in interval notation, open-ended, open interval, written this way. You should be able to see this besides having to hold the stick up in the air like I was doing earlier to get a sense of this. You should be able to look at this ratio here of y, by its definition, y over x, and realize that x could become 0. And if you're dividing by 0, you have an undefined value. And the ratios of y over x can be either positive or negative. Okay, so that should make sense to you in the ratio sense, and it also should make sense to you in the sense of thinking of the slope of this terminal side. Okay, those are some more properties. Why don't we go ahead and end this segment, and then we'll start talking about practicing, or we're probably only going to get through one